Good morning.
Hello, sir.
Hello.
There were 9 people. Now there are only 8. Somebody left. Okay, let's start. So last class, what did we see? Last class, we saw R trivial and L trivial languages, and we saw some characterization plus automata plus expression slash expression characterization. Did you do it the exercise for L trivial? What is automata model for L trivial? I think nobody has done it. Please do the exercises, otherwise it will become difficult.
Sir,
Yeah.
so I tried the exercise, but I was not exactly sure what the model of automata like exactly means. So one model I came up with, so as we define for a DFA,
Yeah.
we just kind of define like from the basic definition of DFA itself, we define it to read the word backwards.
Okay.
And then the entire, I mean, since if L is an a regular language, then reverse of L is also regular, so all the automata theory which we do on usual automata will go through,
Yeah.
and then that automata would recognize L trivial
Okay. Yeah.
languages.
That's
But I
all.
mean, I thought it was kind of cheating, because I mean, I'm just redefining automata from the start, so I don't know if that.
Okay. 1 second. Okay. Yeah. What you're saying is right. You don't. You just need to read the word from left, right to left. All right. So that is L trivial and R trivial. Now today we are going to discuss something. We won't get into Simon's theorem, but I'm going to. Uh, we are. I think we'll today see the definition. Okay, so let me start with the correspondence. FO less than is equivalent to star free is equivalent to periodic monoids. This is the Sulzberger's theorem. Okay. Now we are going to look closely at FO less than. I'm going to look closely at FO less than. So um, what is a parameter on which I can build a hierarchy within FO? Yeah, I want to see a periodic monoids. A periodic monoids. Now, for me, right now it's like a block, but I want to see them closely. So I want to define a parameter on which I can say, okay, this formula is simpler than this formula, or this formula is more complex than this formula. Such a parameter, there are many parameters. For instance, quantifier depth is a parameter. Okay, you can see that F4 formula of some fixed depth quantifier depth. I hope all of you know what is a quantifier depth. So as quantifier depth increases, you can specify more and more complex conditions. But ideally, what we want is that we want a parameter which has significance in all these um, classes that cut across these classes. And such a parameter exists, that is quantifier. Any guess?
Depth.
Yeah, quantifier depth is not a good parameter because it doesn't have much significance in monoids.
So alternation.
Yes, alternation. Who said that? Dhruv?
Yeah.
All right. Quantifier alternation hierarchy. What is this? So any formula can be written in Prinix form. Let me tell you what is that. So for instance, if I have a formula, there exists x for all y, x less than y, and b of y, and there exists y, x greater than y, and a of x. I have such a formula. Imagine I have such a formula. Okay. I'm bracketing it fully so that you understand. So for instance, uh, yeah, so I have their axis and then one for all y, then another their axis y, and so on. So how do I make it into Prinix form?
We can rename y by z, like one of the y's by z, and then bring it out in the outermost quantification or
Yeah.
the form.
Yeah. So the problem is that if I pull this y outside, then these uh, if I mean, right now I can't put both y's outside because then it will, I mean, these y's will also, for instance, if I pull this out first for all y, the followed by the axis y, then the innermost y will be quantifying these y's. So therefore, first of all, I want to rename this formula. I will rename this as their axis x, then I'll keep this y. I mean, I could do otherwise also, the other way also, but I'm just choosing it to do this way. And then I'll rename this y to be z. So I'll say their x is z, x greater than z, and a of x. And then this one I will rewrite it to be, so this is all equivalent. This one I will rewrite to be their x is x. Then I can pull out this y, and then I can pull out this z, and this will be x less than y and b of y and x greater than z and a of x. Yeah, can do it this way. Okay, so this way, I mean, there is nothing complicated going on. It's just that you have to be little careful when you are pulling out. When you're pulling out across conjunction and disjunction, you don't have to worry. But if you're pulling across implication, then you have to be a little careful. First of all, you have to convert it into and or, and then you have to pull out the quantifier. That's deep. So this is how you convert any formula to Prinix form. So any formula can be written in Prinix form. Now this formula, if we look at this formula, it has uh, quantifier depth 3, and what we are interested in is quantifier alternation. Okay, what is quantifier alternation? So for instance, any FR formula, you can write it as, it either starts with some there exist, and then some for all, then some there exist, then some for all, and so on. Or it could also start with for all, some for alls, then some there exists, then some for alls, then some there exists, and so on. Yeah. This is how any formula will look like. So if the formula starts with there exist, and we count the number of blocks. For instance, if I have a formula like there exist, then for all, for all, for all, there exist. I mean, if it is just there exist, I'll just call it, I'll say it's a sigma 1 formula. Okay. Sigma stands for existence. And so if I have only there exists, I'll say it's a sigma 1 formula. If I have only for all some phi, I'll say it's a pi 1 formula for all. If it is there exist followed by for all, I'll say it's a sigma 2 formula. Similarly, for all followed by there exist, I'll say it's a pi 2 formula. In general, if I have there exists, there exists, there exists, then some for all, for all, for all, some there exists, there exists, some for all, for all. I have block 1, 2, 3, I count up to n, I'll say this is a sigma n formula. It doesn't have to end with for all. I just count, it has to start with there exist, and then there are subsequently n blocks, I'll say it's a sigma n formula. Okay. Similarly, if I start with some pi and then some there exist, okay, and I have 1, 2 up to n, I'll say it's a pi n formula. All right, so I can draw a figure like this: sigma 1, pi 1. The complement of a sigma 1 formula will be a pi 1 formula. Why? Because if I have negation of there exists, there exists x, there exists y, x less than y, if I have a formula like that, what I can do is that I can push the negation inside. So if I push the negation inside, we have a logical equality, like equivalence, like negation for all negation is actually same as there exist. If I say that there exists an x is same as saying that it is not the case that for all x it is not the case phi. Yeah, I hope you, what I'm saying is that there exists x, phi of x is equivalent to negation for all x, negation phi of x. What does this mean? This means that there is an x such that phi of x is true, or there is an even number, is same as saying that it is not the case that all numbers are odd. Yeah. So it is not the case that for every x, negation phi of x is the case. So then you say that there exists phi of x. So if I have this, using this equivalence, what I can do is that every time I push negation inside, that will change it to for all, and it will be negation inside. So it will become for all x, negation, there exists y, x less than y, and this will become for all x, then for all y, negation x less than y. Finally, negation x less than y also we can convert it to x greater than or equal to y, but I'm just not doing it because it doesn't matter to us. So this is a sigma 1 formula, negation of a sigma 1 formula, and this is a pi 1 formula. Yeah. So if I have a sigma 1 formula, its complement will be negation. Similarly, I'll have sigma 2, then I have pi 2, the negation will be pi 2, sigma 3, pi 3, and so on. Okay. And any questions so far? Any questions so far? Okay. Okay, so right now we know this. Pi sigma 1 is a subset of sigma 2, sigma 2 is a subset of sigma 3. Similarly, pi 1 is a subset of pi 2, pi 2 is a subset of pi 3, and so on. Yeah. Now, sigma 1 is a subset of pi 2. Why?
We could simply add a for all quantifier for a variable which is not being used in the formula.
Yeah, because for if I have a formula like there exists x, there exists y, phi of x or phi of xy, I can trivially consider this to be something like there exists pi 2 is what for all there exists, yeah. So I can just imagine that this for all quantifier does not exist there. Yeah, it's or like Dhruv said, you can think of them as some dummy variables. I play some dummy variables which doesn't have anything to do with this formula. I'll just say for all x, for all z, in some formula. So I can trivially see that any there exists formula. I mean, any there exists formula is a subset of for all there exists formula, because I don't care about this. So sigma 1 is a subset of pi 2. Similarly, pi 1 is a subset of sigma 2. Sigma 1 is a subset of sigma 2. Pi 1 is a subset of pi 2, and so on. Okay. This is what is quantifier alternation hierarchy. Alternation hierarchy of XOR. Okay. All right. Let me also introduce another class. If I have a sigma 1 formula, okay, it's like there exists x, there exists y, phi of xy. And if I have a pi 1 formula, which is like for all x, for all y, phi of xy. What is a class which contains both of them?
Pi 2.
Sigma 2 contains both of them, pi 2 also contains both of them. Yeah. But these classes have a problem that they are not close into complementation. Pi 2's complement lies in sigma 2, sigma 2's complement lies in pi 2. So right now I'm only talking about formulas, syntactically about formulas. I'm not talking about definability in terms of languages. It might turn out that every formula can be written in sigma 2 or something like that. It might. It is not the case, but a priori we don't know that it is not the case. So right now I'm talking about syntactical things. So if I consider Boolean combinations of sigma 2, sigma 1, of sigma 1, Boolean combinations of sigma 1, what will be that? It will be, I can say if there exists x, there exists y, phi 1, and negation negation of a sigma 1 formula will be in pi 1. Yeah, so I can actually write pi 1 formula for all z1, for all z2, phi of xy, or uh, there exists z psi of x, psi of z. something like that, some formula like this. Now, if I take its negation, it will be again a Boolean combination of sigma 1. Yeah, because if I take the negation of this formula, I can apply De Morgan, and then what will happen? So this, there exists x, there exists y, phi1 will become for all x, for all y, phi negation phi1. This one will become there exists z1, there exists z2, phi1 of xy, and so on. But all these formulas are again in Boolean combination of pi1, is either in sigma 1 or in pi1. So this class we will call B sigma 1, Boolean combinations of sigma 1. Sigma. We could also write it as B pi 1, but it is easy to say B sigma 1. That's why we say B sigma 1. Yeah, you could as well say B pi 1. There's nothing wrong with it. So now we can refine this picture, the earlier picture we drew, a little bit. We can say it is like this: sigma 1, pi 1, B sigma 1, sigma 2, pi 2, B sigma 2, and so on. Okay, you can actually refine this picture even more. If you, how many of you studied complexity theory course? In complexity theory, when you do the hierarchy of um, uh, let's imagine you are talking about polynomial space, then you have a class like sigma 1 pi 1. Then you will, the next class will be sigma 2 intersection pi 2. Yeah, instead of B sigma 1, you will have the sigma 2 intersection pi 2. Form or classes or formulas which you can represent both are sigma 2 and pi 2. You typically call them delta 1, delta 2, and so on. Yeah. But for us, yeah, I mean, at the moment, we are not interested in those classes. Those who are doing in FO2 will know that FO2 has a characterization like one of those classes. Okay, so this is what is quantifier alternation hierarchy. Now, it's a long-standing open problem in algebraic automata theory to characterize each of these classes. Okay. But so far we have managed, there are infinitely many levels of this class. We have managed so far to reach till sigma 5. If I remember correctly, sigma 5 we have reached. And beyond, and that itself has taken something like 50 years to reach till level 5. And for us, we will, the major classes which we will see today, we will try to see sigma 1 and sigma 1 characterization, and B sigma 1 characterization is called Simon's theorem or piecewise adjustable languages. Okay, I mean, so far you might think that it's very these are very made up classes, because I mean, why would anybody think of a language in terms of formulas? But these are not made up classes. You will immediately see that they are very nice looking classes. So let's try to look at what is sigma 1. Sigma 1 formula. Let's try to write a formula in sigma 1. Can somebody give me a formula in sigma 1? Which means something. Give me a formula in sigma 1.
There exists x, ax.
There exists x, ax. What does this say? Let's write a regular expression for that.
Sigma star a sigma star.
Yeah, I'm going to write capital A for this. So A star A, A star. Yeah, it just means that there is a letter A. Give me another formula.
For all x not of
No,
ax.
we cannot say for all because it's sigma 1.
Oh, sigma 1. Okay, yeah. Um,
Right now we have
It's
only,
11 o'clock.
we have only used one variable. Give me another variable.
There exists x, there exists y,
Yeah,
such that ax
yeah.
and by and x less than y.
Ax and by and x less than y. Can we write a regular expression for that?
A star A star B, A star.
A star A, A star B, A star. Okay, so now can we write another formula, or can you give me how generally sigma 1 formulas will look like? What are the languages accepted by sigma 1 formula?
Boolean combinations of languages of this form, maybe.
Boolean combinations of,
Languages of this form, A star, some letter A star, some letter A star, some letter A star.
yeah, but where did you get Boolean combinations? Because if you want sigma, the class sigma 1 is, do you think it is close to the complementation? Because if you complement a formula like this,
Yeah, right. Yeah, sorry.
No, so I think it can be conjunctions or disjunctions,
okay, conjunct,
because
yeah,
any sigma 1 formula in that we can so we have like a string of there exists quantifications, like existential quantifications, and
yeah,
there inside there's a sigma 0 formula, like like either conjunction or disjunction of sigma 0 formulas.
yeah.
So probably we can have disjunction and conjunction there.
Yeah, so let's try to see. So typically, this is how you manipulate formulas. Yeah. So I will start assuming that my prefix is like there exists x0, or there exists x1, there exists x2, there exists xn, and then I have a formula phi of x1 up to xn. Yeah. This formula I can try to write it in CNF, conjunctive normal form. Okay. Instead, I'll write it in DNF, disjunctive normal form. What is disjunctive normal form?
Disjunctions of conjunctions.
Yeah, disjunction of conjunctions. So now let's look at what this formula says if it is in DNF. So it is going to say that there exists x1 up to there xn. Then it is going to say that either this or this or this. Now each of these will be like x1 less than x2 less than x3 less than xn. That is one possibility. I mean, if I have, just imagine I have a formula like a of x. Okay. What I can do is that if I have just a formula like a of x, what I can do is that I can I can rewrite it as a of x and x1 less than x2 or x2 less than x1 or x1 equal to x2, something like that. Yeah. This a of x is equivalent to a of x and x1 less than x2 or x2 less than x1 or x1 equal to x2. Then I can distribute this conjunction over this disjunction. So then I'll get a of x and x1 less than x2 or a of x and x2 less than x1 or a of x and x1 equal to x2. Yeah. So using this technique, what I can do is that I can assume that every disjunction here, every conjunction here, sorry, no, every disjunction here is of the form x1 less than x2 equal to x3 less than x4 and so on up to some extent. I mean, the real, I mean, the variables might change, like x2 might be less than x1, which might be equal to x3 and so on. But I'll get a sequence of variables and then I'll say, what are the possible labels for each of them? I'll say a of x1 and b of x2 and b of x4 and c of xn and so on. So I can assume that every conjunction is of this form. Every disjunction is a conjunct of this form. Are you following me? Are you following me?
Yes, this is fine.
So therefore, this disjunct is actually equivalent to saying that A star, A star, B, A star, B, A star, C, A star. Because all we are saying is that there exists some positions x1, x2, x4, up to xn, so is that x1 is labeled by A, x2 is labeled by B, x4 is labeled by B, and xn is labeled by C. So I will write this conjunct as this. Similarly, all other conjuncts, I will be able to write it as some A star something, some A star something, so on. Or yeah. So therefore, uh, let's give a name to such a thing. Um, so there are many ways you could say what is this. For instance, A star, A1, A star, A2, A star, AN, A star. This thing has many properties. Can you give me some of those properties?
No, so I have just one question.
Yeah.
Essentially, you're saying that any disjunct, in that if we have an ordering part of the formula,
Yeah.
you can reduce that ordering part into multiple disjunctions where the ordering is now a total order on the free variables.
Yes.
Okay, I see. All right.
That is just a simple manipulation of the formula. This is how you will.
Right, right.
This is how. I mean, from a logical formula, you come to the corresponding expression of languages. This is how you do it. You will actually enrich the formula so that you get a nice form by just first writing it in conjunction of CNF or DNF and then adding these formulas. Yeah, and then finally saying that, okay, look, this formula is a language of this form, and therefore, yeah.
So you once said that the star freeness also holds for tree-like structures as well. But I think there the proof of equivalence with sigma 1 won't hold, right? Because this is very specific to words.
No, we don't have the star-free expression for trees. That's what I was saying. Star-free for trees is an open problem.
Oh, yeah, my bad. Sorry, I meant scattered linear orders and stuff. So
Yeah, yes, yes.
so there a similar strategy will work, is it, or does it even make
Yeah,
sense?
everywhere. This is a standard idea. Whenever you have to manipulate some formulas, so I mean, only for very simple cases, such techniques will work. For instance, if you are doing with a sigma 1 or sigma 2 or FO with two variables or something like that, you will always do such manipulations. But
I
for
see.
complex formulas, you will have to go into more complex techniques uh, Ehrenfreich Fraser games or such kind of love to go. Yeah.
Okay, thanks.
Model theoretical techniques. Here I'm just manipulating the formulas and I'm saying that look, every formula I can write it in this form. Okay, so let me give a name to this kind of expressions. So a language of this form, I'll call it as a shuffle ideal. or in Generic actually calls it a simple language, and so therefore, what you will get is that, so this kind of language we'll call it as a simple language. So what it says is that A1, A2, so this one says that all words containing A1 to AN as a what?
Subword.
Subsequence or subword?
Yeah, as a subword. Okay, so such a language we'll call simple language. So what can we say? Sigma 1 formulas, sigma 1 is equal to union of simple languages. Simple languages. Is that clear? That sigma 1 is equal to union of simple languages?
Yeah.
Okay. So it is a little more than that. We'll come to that because this has to do with some pretty heavy stuff. Okay. Now, how much time I have? Yeah. All right. Let's observe some couple of things about uh, union of simple languages. Okay. So ultimately, what we want to say is that we want to give a characterization for sigma 1. In other words, I give you an FO formula and I ask you this question: is it in sigma 1? So you should be able to tell me if it is in sigma 1. So at the moment, we are not yet there because we just characterize sigma 1 languages as a union of simple languages, but still we don't know how to check if a given FO formula or a given Shortly language is a simple language. So we have to work for that. I don't know if we will finish today, but let me let's get on with it. So okay, so one of the properties of a union of simple languages, we are going to call it so let me introduce shuffles. Shuffles. So what is this operation? We'll write it as this. So L1 shuffle L2 is set of all U1, V1, U2, V2, etc. UN, VM says that U1, U2 up to UN is in L1 and V1, V2 up to VM is in L2. What is shuffle? So for instance, if I have, let's imagine L1 is the word AB and L2 is the word XYZ. So then L1 shuffle L2 will be, I have a number of words. So first it's AB, XYZ, then A, X, B, Y, Z, then A, X, Y, B, Z, then A, X, Y, Z, B, similarly, and so on. Yeah. So basically, we mix uh, we mix the words in L1 and L2. So all the way up to X, Y, Z, A, B. Okay. So they need not be on different letters. They can be over the same letters. That's what is shuffle. So exercise. If
Why are N and M different in your definition?
it
Shouldn't that be?
need not be same. That's all.
Mm,
No, but they will be same, right?
I don't understand the dot 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 if they're not the same.
Actually, M can be like N plus 1 or something, or maybe N.
How would that work?
Yeah. Sorry. I made a mistake. Yeah. So basically,
And is
what I wanted to say was that some of those words could be empty. Yeah. But the way I wrote it, I have to use the same index. What I meant is that some of the, for instance, B2 could be the empty word.
even if the
But
language does not contain an empty word?
No. Even
Even if the language does not contain an empty word, it can still be empty, is what you're saying.
no. The entire word has to be in L2. V1 up to Vn has to be in L2. So I'm saying that UIVI is in A star. Okay. So for
but if uh,
If
empty, you will remove it. No, if you have V2 suppose empty, then you will combine U2 and U3.
yeah, you will combine U2, U1 and U3. But the way I have written it as U1, V1, U2, V2, and so on. So I'm actually interspersing that.
okay,
Like
I'm still confused. So in your example, XYZ AB is allowed even though L1 and L2 do not have empty words, and the first word ought to be from L1.
yes, exactly. That's my point.
Okay.
So L1 shuffle L2 doesn't mean that the word has to start with L1. It doesn't mean that. It just means that uh, um when I read, I have two words. I have this. If I'm given this word, I can pick up some words, some positions, and rest of the. So I can pick up some of the positions. Let's call it that set X, and rest of the positions will become set Y. The word over the position X will become a word from L1. The word over the set of position Y will become a word of L2. That's all it means. It doesn't mean that it has to start with L1 and it has to end with L2. It doesn't mean that. Is that clear?
Yeah,
So
yeah.
one way to write it would be L1 union epsilon, right? In your definition, if you put U1 through UN are in L1 union epsilon, and V1 through VN are in L2 union epsilon, would that be right?
No, I think he's trying to say the concatenation of UN to UN
Yeah,
is in
so
L1.
I don't think it's U1
Oh.
to UN as in like U1
Okay.
comma
Right.
U2 comma UN. It's just
Right.
one word.
Yeah. So let's try to prove that. So that is the best way. If L1, L2 are regular, so is L1 shuffle L2. How do we prove this? If L1 and well,
Take
then
the finite state automata for both and non-deterministically switch between them.
yeah. So basically, what we can do is that I get L1, I get an automaton A1, L2, I get an automaton A2. And what do? I take the product automaton Q1 cross Q2. And on a letter, if I'm in state PQ, on a letter A, I choose which one I'm going, which way I'm going. If I'm going, either it is going to be P dot A comma Q, or it is going to be P comma Q dot A. Yeah.
Yeah.
And so initial state is some Q0, Q0, Q. Initial state is some both initial states of A1 and A2. Final states is again for both final state F1 cross F2 of L2. Yeah. So that is how you show that L1 shuffle L2 is regular. Yeah. So now we are interested in a shuffle ideal. Ideal is a shuffle of the form L shuffle A star. Okay. Why is it called a shuffle ideal? So what does this mean? L shuffle A star. So the thing is that shuffle ideals.
So L shuffle A star would just be we take any word in L and insert random alphabets anywhere in between.
Exactly. So another
Isn't same as upward closer of L?
exactly. So we could say that shuffle ideals are closed under superwords. Superwords. What does that mean? That means that if K is a shuffle ideal, if U is in K and U is a subword of B, then B is in K.
But I don't see why it's called shuffle ideal. Like, is it behaving like an ideal anywhere?
Yeah, so the thing is that we could actually use upward close set, but the word ideal is used in the sense of upward closed.
Right, I see. In the partial order, the upward closure thing.
The subword order. Okay. So it is not used in the sense of a semi-group ideal we have been using so far.
So whose terminology is the shuffle ideal?
It is generic past terminology, but ideal is used quite common. I mean, next what we are going to see is that we are going to see ordered monoids. And in ordered monoids, whenever you take a set, you actually use the terminology ideal for an upward closed set. Okay.
Wait, upward closed sets are ideal. You call them ideal.
Yes, exactly.
Okay. Yeah. This is very weird because there is another group of people which calls downward closed sets ideal.
Yeah.
Okay.
Yeah. Okay, so now um, okay, so it is clear to you that it is upward closed. The reason why it is upward closed is very simple, because if I have a word from L, then I can always insert any letters from A star. Any words from A star, I can insert to any place. So therefore, if I have a word, then I can insert more and more letters to any place within any two letters. That's why it's upward closed with respect to the subword order. Now, a remarkable fact about such a set is that any shuffle ideal or any set of this form any shuffle ideal is a finite union of simple languages. Why is it? What are we saying? We are saying that you take any upward closed set like L shuffle S star. L might be an infinite language. Yeah, it might have infinitely many words in it. But the moment you shuffle it with A star, I can actually write it as some finite union of languages of this form. That's remarkable. Yeah. So, and if we make use of this proposition, let's not prove this proposition today. We will rest it for some time and then we'll take it. So if we take this proposition, when I can say that sigma 1 is actually equivalent to shuffle ideals or upward flow sets. Yeah. Why is it this proposition is true? I'll tell you the reason why it is true. Why it is true is because of a fact called Higmann's theorem, which says that there are, if I look at A star with respect to subword ordering, there are finitely many minimal words. What am I saying? If I have A star and I'm looking at words with respect to subword ordering, then there are only finitely many minimal words with respect to the subword ordering. In other words, you take any set, there are only finitely many incomparable words in that set. Incomparable words are precisely the minimal words. Okay, so you take any set, you will be able to find some finitely many words which such that any other word can be represented as a super word of these minimal words. This fact is known as Higmann's theorem. It has a simple proof, but this area is called well quasi orderings. The such theorem exists. The most famous of such theorem is called Robertson-Seymour theorem. Finite graphs with respect to the minor ordering is a well quasi ordering. That's what Robertson-Seymour theorem says. Same thing. That if you take all finite graphs and you consider up to the minor relation, then there are only finitely many minimal graphs. Similarly, there is a theorem called Driscoll's tree theorem, which says the same thing for trees. So, well quasi orderings is a well-studied area of computer science. I mean, these results have huge applications in verification and all kinds of things. Uh, so that's why we can look at that Hickman's proof of Hickman's theorem another day. But for today, we can do a simple automata theoretic proof. The proof is very simple. If I have a shuffle ideal which is regular, I'm going to assume that the shuffle ideal is regular. Okay, and it need not be a priori regular, but we are assuming that I have a shuffle ideal which is regular, because I know that for a fact all languages accepted by sigma 1 formulas are regular. So I can assume that sigma 1 formula, I can assume that I have a shuffle ideal which is regular. Okay, so then I actually so imagine I have k is equal to k a star, k shuffle a star. So this is actually saying that k is a shuffle ideal. Or let me call it L. Okay, I have an automaton for k. This is my automaton. Let's imagine L has an automaton with n states. N has an automaton with n states. Let k equal to all words in L such that length of U is at most n. Okay, so what is my idea? I'm going to consider all words of length n, and I'm going to say that any word in L is a super word of a word of length at most n. All right. What is the reason? If I consider, let's consider a word in L such that W is a word length greater than n. So then what I can do is that so this I'm going to say going to be minimal and complete automaton. Don't know if we require that, but
What are we trying to prove?
I'm trying to prove that if I have any shuffle ideal is a finite union of simple languages. But
Okay.
okay.
Yeah.
Basically, what I'm saying is that I'm taking an automaton for L, and it has n states, and I am taking all words of length at most n.
I think we're proving a special case, right? That any regular shuffle ideal is a union of.
Yes, yeah, I'm proving a special case, which is any regular shuffle ideal is a finite union of simple languages.
Right.
No, but all shuffle ideals are regular.
All shuffle ideals are regular. That is true, but for that you need Hickman's lemma.
Okay. So we are okay, fine.
So we are trying to prove this without using the existence of n minimal or finitely many minimal words, is it?
Exactly.
Okay.
Okay. So, I mean, this proof is very simple. What it says is that what I'm trying to do is that I'm saying that any word of length greater than n is a super word of length word at most n. And what is the reason? So imagine I have a word of length greater than n. Then it has a run. It has a run like u0, then some Qn of W has a word of run of this kind, but there are only n states. But this run needs to have length n plus 1. So there is some state which is repeating Q, Q. Yeah. I'm taking a word of length at greater than n. I know that n greater than n means that the run's length will be at least n plus 1. So there will be a state repeating in its run. It's a DFA I'm taking. Okay. So if I chop this portion of W off, if I chop this portion of W off, then I'll get a word. I'll get a word which is smaller than n.
Yeah, you're right. Essentially, we are getting the automaton by chopping out all the loops, self loops.
Exactly. 1 second.
So this is kind of just exactly the thing which we did for proving pumping lemma, right? Except for pumping up, we are just pumping down the middle.
Exactly. Exactly. Okay, so let me just.
Also, that now we are pumping down at various locations, not just one.
Yeah. So basically what I'm saying is that if I have a word of length greater than n, then I can actually get rid of uh, the portion where the state is occurring twice. Okay. And if I chop it off,
So
yeah.
we can just use pumping lemma to prove this, right?
No, you cannot use pumping lemma to.
So for regular languages, we know that there exists a pumping length.
Yeah.
Such that any word which is bigger than the pumping length can be written as XYZ.
Yeah. No, I mean,
the middle word is non-empty.
Yeah.
And if XYZ, for that word XYZ, which is in the language, X, Y to the NZ is also in the language for N greater than equal to 0.
Yeah, that is true.
So we just take N equal to 0 and remove that Y, and we'll get XZ, which is a smaller word, which is also in the language.
I think that's pretty much what he's doing, right? And pumping
yeah, I mean, we are just repeating the proof of pumping lemma here. That's what I'm saying. We can just use the lemma and say that we are done.
Yeah. So here you just have to be a little careful because you want to. Yeah, you'll have to do this repeatedly to get to a word of length atmosphere. Yeah. So basically, you take a word whose length is greater than n. Then you will be able to find two states which are repeating. So then you chop that portion of the word off. So then you will get a smaller word. If the word's length is still greater than n, you repeat this procedure till finally you will get a word of length atmosphere. Yeah.
Yes.
Okay, so then you will get a word, and this word, so any word of my shuffle ideal L can be seen as a super word of this language. Super word of a word from this language K, which are namely all words of length atmosphere. And therefore, I can write L as union of symbol languages of words from K. That is one proof that I can actually write it as union of simple languages from a finite set of words. All right. So we already saw that sigma 1 is upward closed set. and therefore sigma 1 is a finite union of simple languages. Now the big question remains is how do I check if I am given a language and I asked if it is a finite union of simple languages, how do I check? And there we have to go back to monoids. We have to go back to monoids.
So now we are trying to prove the converse direction.
No. There is no converse direction. I know that sigma 1 is tuple ideals.
Right.
My question is, can we have a algebraic characterization?
Okay. Okay.
Okay.
Yeah.
How do I check? Or in other words, it is decidability of sigma 1. Decidability of sigma 1. Okay, so now we take a small detour. This is something which we didn't do when we were doing monoids. You might have seen that there were ordered monoids, and we didn't touch upon ordered monoids because I was delaying it because initially we do ordered monoids. It's not going to be useful. So what is the idea? So the other day when we looked at R-trivial languages, we know that R-trivial languages is not a symmetric class of languages. Yeah, it's not symmetric. It's a unidirectional class. So you do reverse or you do it is closed under union, intersection, complementation, left quotient, right quotient, everything, but it's still not symmetric. And to characterize an asymmetric class, we used an idea. We used the idea of imposing an order on the structure of imposing an order on the model we are interested in. Yeah. So this idea is fairly universal in automata theory and logic and so on. Whenever you have a class which is asymmetric in some way, the way to characterize is by imposing an order on the kind of things you are interested in, making it directional. So let's look at sigma 1. Sigma 1 is closed under union. Why it is closed under union?
Because union of two finite union of simple languages again a finite union of simple languages.
Yeah. And it is closed under intersection. Why is it closed in intersection?
Because we can take the corresponding sigma 1 representation and then manipulate the formula to get another sigma 1 formula.
Yeah, exactly. For instance, I have two sigma 1 formulas. I merge them. So that is very easy. I just write it as a conjunction and then I make it into prenex again. And then I again write it in descending normal form. And I do all the tricks which we discussed. And then finally, again, I'll get a this one. Again, I'll get a sigma 1 formula. Okay. But not under complementation. For instance, if I have A star, A star, and I want to take its complement, there is no way I can write it as again in some as a simple language. Yeah, because no matter whatever I say, what I want to say is that A does not exist in my world. That cannot be said as these words should exist in your world, because this is a complement of the kind of conditions we have dictated. So there is no way you can show that this is sigma 1 is not closed in the combination. So now how do we characterize sigma 1 as a class of monoids? So now we come to a problem. So if I have, let's imagine I have a language L in sigma 1, and imagine I have a monoid which recognizes L1, L, using the set P. Okay, so H inverse of P is equal to L. So if I can just complement P, P complement will be L complement. Yeah, that is the normal way of things. By complement the accepting set, I'll get the complement of the language. So therefore, if you do the normal way, that means if I take any accepting set, if I am allowed to use any accepting set, then the classes which I am interested in will be close to the complementation. So what I'm saying is very important. What I'm saying is, if I'm allowed to use any accepting set, then the languages which I can recognize using a monoid will obviously be close to the complementation. So I cannot allow them. Okay. Therefore, how will I do that? And that is where, again, the idea we use for L-trivial and R-trivial classes come into picture. I'm going to impose an order. Okay. We are not going to impose the order in the same fashion. We are going to impose order in a different fashion. So here comes the idea of ordered monoid. What is an ordered monoid? I have a monoid and I have an order on elements of it. When I see order, I mean a partial order. Okay, partial order. So the simplest order is M with equality. What is equality? Equality is not everything is equal to everything, because then it won't be a partial order. Equality is I have, let's imagine I have what is equality? Equality is A comma A, B comma B, and so on. That means things are only equal to itself. That's all. Nothing else. Okay. So for instance, if I have a monoid 1A, AB, BA, B, zero, you all know, remember this monoid. This is accepting monoid of AB whole star. I can, one ordering is everything is equal to itself. So A equal to A, AB equal to AB, BA equal to BA, B equal to B, C 0 equal to 0. That's one monoid. Okay, 1 equal to 1. So that's one ordered monoid. So what is this order? Sorry, I didn't say one thing. So not only this is an ordering on the elements of M, it has to satisfy this following property. If X is less than or equal to Y, then U X V is less than or equal to U Y for all UV in N. That means M multiplication preserves order. Okay. Multiplication preserves order. So if I have, how do I prove that x1 less than or equal to x2? y1 less than or equal to y2, then x1, x2 less than or equal to y1, y2.
We prove that x1, x2 is less than equal to x1, y. Yeah, x1, y2, and then which is less than equal to y1, y2.
Not one.
x1, y1 is less than or equal to
y1.
this is what I want to do. So I know that x1 is less than or equal to x2. So then it means that x1, y1 is less than or equal to x2, y1. And x2, y1 is less than or equal to x2, y2 because y1 is smaller than or equal to y2. And therefore, if I multiply on the left by x2, it will preserve the order. So therefore, and since it is a partial order, I'll get that x1, y1 is smaller than or equal to x2, y2. Yeah. All right. Okay. So now, if I have two ordered monoids, M1 with less than or equal to 1 and M2 with less than or equal to 2, what is a morphism between them? Ordered monoid morphism. I mean, all these things carry for semigroups also, ordered monoid morphism. So how does this thing work? H is a function from M1 to M2. So is that what? H of M1, M2 is equal to H of M1 times H of M2. H of 1 equal to 1 and x less than or equal to y implies h of x smaller than or equal to h of y. Yeah, as you would expect. Yeah, ordered monomorphism preserves the order across the monoids.
So, what is the reason behind having that syntactic order preserving thing, like the multiplication preserves order property? Why would you want that a priori?
Because otherwise there is no link between the order of the monoid and the multiplication.
I see. Okay. Yeah, the whole point was to have something like that. Okay.
We are trying to make a directional structure. Earlier, our monoid didn't have a direction in it. We are going to make our monoid into a directional structure. It has a direction in it now. So things are always, I can now say that, look, this is how it should be. It should be always upright. It cannot be, yeah, so that's idea.
Yeah, yeah. Okay.
Okay, so now this is ordered monoid ones. So now let's try to.
Sir, I have a meeting at 12, so
Okay,
will it be
so let's finish here today and we'll
okay?
take it in the next class.
Okay.
I covered a lot of ground, so you have to do this before you come for the next class. Yeah, you have to do little bit of groundwork. I hope it was not too fast for you. When is our semester ending?
April last week, maybe.
April last week. Okay.
I don't know, but maybe it's like that always. So I'm guessing it should be the same.
All right. And by the way, what about your this thing? Presentation topics?
Yeah. So Srisha, Ashwant, and I are going to present the Ramsian split thing that you have sent,
Okay.
and yeah, others can tell about themselves.
Me, Saina, Rishikesh, and Anandu are presenting factorization for us.
All right. And others? Can you? Is there some way you can send me a mail in Moodle, or is there some way I can?
Yeah, I think there's a forum where people can talk to each other. I think so.
Yeah.
We can mail each other on Moodle.
All right.
Or you can have a discussion forum set up if you want.
Yeah. Where in Moodle itself?
Yeah. on Moodle itself.
Yeah. How do I do that?
Maybe Ashwarya ma'am would know, right? It's very easy. Like you just go to the course webpage and you just click on a new conversation thread
All
kind of
right.
thing.
All right. Okay. Okay then. I will start that.
Thank you.
All right.
Okay, thanks.
All right. See you. Bye.
Thank you, sir.